smart sensing, LiDAR and IO link for every operation. It's brought to you by SICK. Let me tell you a little bit about today's presenter. Aaron Rothmeyer is a product manager at SICK, where he specializes in advanced LiDAR technologies for industrial automation and autonomous systems. With a strong background in optical sensing and a passion for innovation, Aaron plays a key role in shaping how sensor technologies are applied across logistics, robotics, and smart manufacturing environments. Aaron has been instrumental in projects that integrate LiDAR into autonomous vehicle systems, including some groundbreaking work in automating yard truck operations. His expertise bridges the gap between cutting-edge sensor hardware and real-world industrial applications, helping manufacturers and logistics providers improve safety, efficiency, and data-driven decision-making. Following today's presentation, we'll have a live Q&A with Aaron, so I encourage you to submit any questions that you have at any time during the session using the chat box that you'll see over on the right-hand side of your screen. Also, we'll be providing our attendees with a PDF version of the presentation. That'll be available near the end of the session, and you'll find that over in the Handouts tab. So thank you so much for joining today. And with that, I'll hand it off to Aaron for the presentation.
Hi, I'm Aaron Rothmeyer, and I'm here to talk about simplifying smart sensing using LiDAR and IO link for every operation. Just as a quick introduction for myself, my name is Aaron Rothmeyer, and I'm a product manager at SICK. I've been working with LiDAR products for almost 13 years now and finding out how they work best in factory automations. The goal of today's conversation is to learn the basics of LiDAR, learn the basics of IO link, and then see what happens when we mix them together. And when we mix them together, there's always things to learn from our experience for implementation, for installation, and I'll try to give you some tips on how to do that. And then finally, we'll have some time for questions and answers at the end. So let's start out with a quick brief on what is LiDAR. LiDAR is based on the time of flight principle. What that means is that a LiDAR sensor sends out a pulse of laser light. It tracks the amount of time it takes to get out to the target and back. And then it determines the distance to the target based on that amount of time. We know the speed of light, we know the amount of time, so we can figure out how far it is to the target. So just a quick animation here. Basically, we shoot out a pulse of light, it comes back, and we just do that over and over and over again. The way that LiDAR works typically is that we then bounce that mirror, or bounce that pulse off of a rotating mirror. So if we run the animation here, we can see basically it just does it over and over and over again to get a range of distances. All of those distances, when combined, are often referred to as a point cloud. And that point cloud can do a wide variety of things, as you might imagine. People do all kinds of different applications using LiDAR data, and those are often used alongside cameras and radar systems as well. Various sensors can be used and fused together in order to get the most reliable system. The thing to keep in mind is that there are differences between LiDAR and these other sensors. Cameras in particular work great in a lot of situations, but are sometimes compromised by changes in ambient light. For example, if you have a sensor, a camera that's out there and somebody opens up a window, or it's a particularly bright day, or you want to transfer to a lights out facility and all of a sudden that ambient light changes, cameras can often have a hard time dealing with that. Radar systems are great too. Radar is a technology that's been around for a very long time. It's very, very robust if you want to use it, outdoors in the rain, things like that. But it doesn't quite bring the same abilities as LiDAR as far as precision goes. LiDAR being, laser precise, often can get down to resolutions under a centimeter, even down to the millimeter level with LiDAR sensors. Whereas radar, I typically think of as a more coarse technology. But again, it does bring that robustness if you've got rain, snow, things like that in the atmosphere. So by combining all of these sensor systems together, again, if you can fuse all that data into one system, you often get the most reliable system overall. But LiDAR brings a lot to the table. When you're talking about LiDAR sensors, there's usually kind of a trade-off between 2D versus 3D. 2D, just like on the slide I just showed, is just a single slice of the surroundings. So like we show here on the right, basically you have a single plane, and then if you have that plane mounted horizontally, you get a reading of everything that it can see in that level plane. If you mount it vertically, you're going to be more like an invisible wall, for example, so you get a vertical plane depending on how you orient that sensor. 3D LiDAR, on the other hand, usually adds some other functionality, whether it's a secondary mirror, a rotating hexagon mirror, or some prism effect, to basically get a 3D view of the surroundings. So multiple planes combined to get one 3D point cloud. Two different concepts, two different executions, but basically all based on that same LiDAR time of flight principle. And the types of applications you get into, having those two different types of technologies can be pretty varied as well. Here I'm showing basically 5 different common 2D applications that I see for LiDAR when we're talking about an industrial environment. I think certainly one of the more popular ones that we see is on mobile vehicles. So if you've got a vehicle traveling through a facility, some of you may already be familiar with a safety portion where you've got a safety sensor on the front of a mobile vehicle, making sure that there's nobody standing in front of it. LiDAR is often used in that safety application, but it's also used in less safety critical applications as well, where maybe the robot just needs to know if a fork truck has parked its forks over the path of travel, or there's cables or racking or something like that that may damage the robot or create downtime. So LiDAR is often used, as you can see on the left here, just kind of like a cow catcher on the front of the vehicle to verify that there's nothing in the path of travel. Similarly, in a static application, we often see LiDAR being used with some combination of totes traveling down a conveyor. Here in this particular orientation, we're looking down into the tote to see if it's empty or full, see if there's anything laying in the bottom of that tote. I've also seen the same thing done where the LiDAR is mounted horizontally over the top of the tote, just basically looking for objects sticking up out of it before it travels onto the next process along the conveyor. Very common way to use LiDAR in logistics automation. And then there's other things that you can find typically throughout a warehouse or an industrial factory as well. We're using that invisible plane just to detect objects in a wide field of view. So you can see here, looking into a robot cell, see if there's something in that area where it's not supposed to be, or looking into a rack to see if there's already a pallet there before loading it. The picture on the right shows a luggage drop area. Some of you may have seen these in some of the airports where somebody comes in and puts in their bag. The LiDAR sensors are often used in those types of applications just to see if somebody has stuck their bag or stuck their hand into that luggage drop area. So anywhere you may want to detect an object, and it could be a large area, that's where we often see these 2D LiDAR sensors employed. Very similar to a light grid, really, an automation light grid, just in a larger scale and as a single sensor instead of having a sender or receiver. 3D changes the game quite a bit when we start talking about 3D LiDAR, and I'm not going to focus too much on 3D for the purposes of this discussion, but just for your information, because we have that additional area of coverage with the 3D sensor, again, we find it in a wider variety of applications. Typically, when we've got a vehicle, for example, and we want a single sensor that just sees everything around the vehicle, many of the 3D sensors are 360 degrees as well, so it's a sensor that you could put, say, on top of a vehicle and get a view of the front and the back and the sides, just all around the vehicle. It's a pretty common application for 3D LiDAR. And then elsewhere within the factory as well, just anytime you need a large volume of coverage, we find 3D LiDAR being used in those applications. So that's a really quick overview of what LiDAR is. Hopefully I shared as much detail as I could in this portion of the presentation. But getting into the next subject, okay, what is IO-Link? IO-Link, despite it being around for a while, I think there's still a lot to learn about what IO-Link can do. As you can see here, basically it was really kind of introduced back in 1993, and there were a lot of changes over the last 3 decades that really made it more common and made it easier to use and more powerful throughout the world. But basically, in roughly the 2010s or 2020s, we started to see some changes that really got it to be as useful as possible. Like any open standard, as it becomes more and more adaptable or adoptable into other field bus networks, we see more and more uptake of that open protocol. So it's a very interesting concept in that from a sensor level, IO-Link doesn't require any additional connectors or wiring or anything like that. There's a very good chance, honestly, that you may already be using IO-Link sensors in your facility and not even be aware of it, because these are often just simple sensors. They don't have any Ethernet cable attached to them or anything like that, because IO-Link operates right over the standard connectors for that sensor. Usually over the power lines and the output lines. So it's just a standard 5-wire connector. And that brings a lot of capability, because that means that now we can get a lot of smart functionality out of these sensors without having to increase the cost and introduce additional cables and additional functions into the sensor. So what that means for LiDAR is that we can basically get a very smart LiDAR sensor into a very simple and low-cost housing. And so from a sensor level, basically what it means is that our LiDAR sensors can now be configured over USB and using a very simple gateway. If anything were to go wrong with the sensor, we can get a cloned sensor up and running very quickly just by importing a new configuration into that new sensor. From a network level, though, there's even more benefits, because now with the network, we can get our simple sensors onto a much more comprehensive field bus network. So we can see here, basically through using masters or gateways, we can transfer that IO-Link signal into all kinds of things, whether it's Ethernet IP or Profinet or EtherCAT. Most of the major field bus networks have some type of gateway available. SICK sells a few of them, as a matter of fact. And oftentimes those gateways often have tools built in to perform logic tasks on board. So it's kind of like an edge computing concept where you can offload some of that function from your PLC and do a lot of it right on the gateway itself, whether it's anding sensor outputs together, or implementing like an OR function, or putting in timers, that type of thing. These kinds of simple logic tasks can often be taken care of right on the gateway. So why do they matter together? Well, that's a good question. Mostly because LiDAR has kind of a bad reputation of being really complex or difficult to integrate. When people think of LiDAR, oftentimes they think of those point clouds, or they think of self-driving vehicles or AMRs, which those are very complex systems, and they do take a lot of time to integrate. But what we've managed to accomplish here at SICK is basically sensorizing that LiDAR and making it a very simple sensor to integrate. And IO-Link is a big part of that, because we're boiling down all of that LiDAR complexity into just a sensor that gives you a yes or no a signal to tell you where an object is or whether an object is present. So IO-Link is what makes it really easy to get that information into that PLC or plant network for analysis. And if you've got multiple sensors, this is a really big benefit. We can actually replicate these sensors without having to go back in and program a whole bunch of sensors by hand. So that ability to connect to a laptop makes a big difference. And I'd like to take a couple minutes just to kind of illustrate that and show you how easy it is to configure the sensor. So what I'm going to do is I'm going to drop out of the presentation here, and I'm going to switch over to our SOPIS interface, which is basically the interface that we use to configure most of the sensors at SICK. And what we've got here is basically a view of the LiDAR sensor that is in front of me. So if I wave my hand in front of it, we can see there's it's basically feeding back all of the measurements that it gets. I'll zoom in a little bit here to make it easier to see. There we go. So what we've got here is basically these blue dots are all of the measurement points I talked about earlier. Remember the animation where we sent out the laser pulses and we got all of those signals back? This is what the sensor sees, is all of these pulses. When I'm in this interface, first thing I need to do is log in real quick, because we do actually start it off in a read-only mode. That's just to prevent anybody with a laptop from coming in and making unplanned changes to our configuration. So I'll log in, and now I can actually change what it can do. If I come over here to this field evaluation tab, this is kind of where the magic happens. I'll zoom in just a bit more because we've got 2 default fields in here already, and they're pretty small, so I'm just going to zoom in a little bit more. Now, if I want to modify those fields, it's not too hard. I can come in, I can just click on one, and then these field points are how I modify the shape of that field. Now, these fields can be basically set up to look like whatever I want. If I want to make it a hexagon or a large rectangle, I can do that, and they can overlap each other as well. So I can make a large field if I need to, or I can add more field points, and I can delete field points. I can make all kinds of changes in here to make that field look like whatever I want. So if I'm looking over, say, a palette, and I've got a standard size palette and a Euro size palette, I can have 2 different fields in here and not have to really adapt anything as I switch from one palette to another. Whatever you want this shape to look like, we can make it look like. If I need to make some changes to the way that it detects those objects, I can do that in here as well. Just as an example, one thing I can do is I can set the response time so that an object has to be in that field for a certain amount of time before it actually triggers. By default, we've got it set to 345 milliseconds. I can speed that up or I can slow it down depending on what the process I'm working with is. We can also set what's called a blanking size. And blanking size is basically how big of an object needs to be present before it triggers the field. By default, set to 200 millimeters, approximately 8 inches or so. I can make that quite a bit smaller. So we've got this set to a response time of 200 millimeters now, and we've got the blanking size set to 25 millimeters. I'm going to change that real quick just to get any noise out of the environment, because I think I've got something in my field of view. But once I've got that set the way that we want it for the application, we can now see on the right there's a green field indicating that's clear, and if I put something in front of it, it turns yellow to indicate something is present. And that right there is what we mean when we say sensorized LiDAR. At this point, I can press download, I can walk away, and the sensor is now configured. It doesn't take any longer than what I just showed you here. Once you figure out what your application is and you've got your parameters set correctly, it's good to go. And that information is now sent out over IO-Link. So now if you need to get that information into, say, your Ethernet IP network, for example, you pair that with a gateway and you're set. You've got a LiDAR sensor that brings all of the power of LiDAR onto a very simple open network called IO-Link. If we wanted to set the other field, we could do that as well. We can set it with other parameters, or we can keep the parameters the same, just depending on what your application is. So now that we've got the sensor set up the way that we wanted, I wanted to show you real quick one of the big features about IO-Link that makes it a really powerful tool for you. Thing to keep in mind is that things happen on a factory floor, sensors get damaged, things fail over time. So when something happens to your sensor, being able to replace it quickly can be a big benefit. The way that we've got it set right now, if this is our application, what we can do is we can take this information, we can share it with our desktop. So wherever we want to store this file, we can create a file on our computer, whether it's on a flash drive or on a server or just on your laptop. And you can put that on your desktop, and then if anything should happen to the sensor, we can clone it very quickly. So just to show you what that looks like, if I come back here, I've got this sensor here, and you can see the serial number ends in 0279. If this sensor gets damaged, somebody comes along and clips it with a forklift and it gets smashed, I can pull one right out of the box, which I'm hooking up now, and I can connect to that sensor. I'll come in here, and you can see if I go online, this new sensor takes a few seconds to start up, but basically, if I read these parameters, you can see we're now on a new serial number, new configuration, clearly not the same one we had earlier. If I need to clone that to look just like my other sensor, I can just import that file that I created earlier. So I come back here to the desktop, I double click on that file, and before too long, I'm back up and operational. We're right back to where we were. This is a clone of the original sensor. So I just wanted to show you that because you saw how quick and easy it is just to get this thing back up and operational under a minute, and you're back to where you were. So that's one of the biggest features I think about IO links though. So getting back into the presentation real quick, I just wanted to share a little bit more about what we typically see when we talk about LiDAR in industrial automation. Looking at what I just showed you in SOPIS, you can see where that type of application could be performed on a conveyor, right? Because warehouses have miles and miles of conveyor, and oftentimes it's difficult to track if an object has fallen off that conveyor. So as you can see here on the left, we've got a conveyor application shown where if you mounted these sensors underneath the conveyor, you can get a very quick view of where an object has fallen off of the conveyor. Set up your zones to be a rectangle along the length of the conveyor. Orient this so that's probably a horizontal plane, and you've got basically a big invisible floor that if a box falls off the conveyor, it's going to pass through that invisible floor, hit the real floor, but you, over your IO-Link network, get an output that says something fell off. And that can save a lot of time and troubleshooting effort in figuring out where that package left the conveyor. So we see that a lot with the TIM, and pairing that with IO-Link makes it easy to wire and easy to install so that you don't have to run a whole bunch of wires back to your PLC. You can just use a gateway to basically pair up all of those and put it out into a field bus network. The other place we see a lot of TIMs installed is on spiral chutes or just chutes in general, where if there's a jam, oftentimes those packages will pile up until they create downtime and somebody's got to go there and clear them all out. We can get kind of a preemptive signal where the TIM is placed over the spiral chute, and by creating a field over the top of that chute, we can find out if something is there piling up so that the conveyor speed can be slowed down, or a light can be triggered to have somebody come out and clear that jam. So those are just two common places that we see the TIM being used in logistics automation. Now, every system for the most part has some drawback when you're trying to install it, whether it's dealing with lighting or dealing with alignment. We've seen some things over the years that we've kind of wanted to call out to make things easier to install when we're dealing with LiDAR and IO-Link. One of the big ones is just picking the right sensor for the job. What we're showing here is the TIM 150 that I'm working with today. And the TIM 150 is a great sensor. There are two different varieties available of it. One's called the TIM 100 and one's called the TIM 150. And basically the only thing that changes between the two is the range. Where the TIM 150 has a range up to 10 meters, the TIM 100 has a range of up to 3 meters. So just basically picking the right sensor. If you've got a large amount of area to cover, you may want to go with the TIM 150. If you've got a smaller zone, maybe you just want to look over a pallet or something like that, that 3 meters may be enough for you. You can get away with the TIM 100. Regardless, TIM 1 series has a whole bunch of other things that we can cover. One of the most important is probably the ambient light immunity, where using our technology called HDDM+, we can filter out any kind of ambient light shifts that might happen within the facility. Very high ambient light immunity, so if you happen to have a change in the lighting in the plant, or somebody opens up a garage door and you end up with more light than you were expected, it's not going to trigger that sensor. It's also not going to get confused by, say, reflective vests or something like that, the high-vis vests. If those happen to be traveling by, it's not going to get triggered based off of those either. So picking the right sensor for the job is a great place to start out when you're trying to get a reliable system with easy implementation. The other thing to consider is that we've got 2 other tools to make things easier when you're trying to get these installed as well. On the right, this is a tool called the Alignment Aid, which solves one of the bigger issues with LiDAR, which is that you can't see the plane. It is an infrared plane, infrared lasers, and so if you're trying to align it, it can be a little tricky, especially if you're trying to do it over the 10 meters that the TIM can see. So we've designed a product called the Alignment Aid tool, which if we switch to a top-down view, I can show you real briefly how that works. Basically, this alignment aid here is developed by SICK and manufactured by SICK, and it's got a series of infrared detectors running the length of the tool. And if I present it with infrared light here, you can see we've got red LEDs that light up wherever the plane is. So by getting 1 or 2 of these and putting them into your facility when you're trying to install it, it makes it a whole lot easier to figure out where that plane is. So just a little trick that we've developed in order to make this a little bit easier. Switching back to the presentation, the field teach-in is another tool that we can use to make things simpler. I showed you how quick and easy it is to create a field. Depending on the shape, it's really not a complicated process. But we do also have a function called teach-in, where basically in the SOPAS software, we can set up the ability to, by clicking a button, basically learn the environment. So if you've got a really complex shape you're trying to match or create a field in, you can press the teach-in button and it'll basically learn that shape and then just give you a signal when something enters that area. So in some situations, it can be a little bit easier to just go with a taught-in field versus designing one yourself. So that's basically it for how we would go about implementing one of these. Again, by combining the power of LiDAR into a simple sensor and then adding IO link to make it easy to network and easy to diagnose and easy to configure, we find that basically the time is right for this smart sensing solution. Thank you very much. And if you've got any questions, we can get to those now.
Well, thank you very much, Aaron. Awesome presentation. I love learning all kinds of stuff about sensors and IO-Link especially. It's really good stuff. I just want to remind the audience that there is still plenty of time to submit your questions using the Q&A box that's over on the right-hand side of your screen. So Aaron, are we ready to tackle a few of these questions that I see coming in?
I am, yes, absolutely.
All right, so the first question on our list is asking about processing. It says, how much processing speed and storage is needed for LiDAR versus, so comparing it to camera optical scanners?
Okay, so compared to camera optical scanners, how much processing speed and storage is needed? That's a very, very good question, very insightful. Cameras in general output a lot of data. Big frame rates and everything like that adds up to a lot of data that needs to be processed and stored.